Good evening. Thank you very much for having me, and great to see such a fabulous turnout at this Perth branch meeting of Renew. My name is Sid Thoo. I am an architect, and I'm going to be talking about some eco-effective design principles that can help you make your build or renovation more energy efficient, more sustainable. Just like to clarify that while I'm an architect, I'm not one of those kind of architects. If you're familiar with what I mean, have you heard the story about the guy standing in a field and then this hot air balloon kind of flies over and the guy in the hot air balloon says, "Excuse me, mate, I wonder if you could help me. I promised I was going to meet a friend and I'm running late and I have no idea where I am. Can you help me? Can you tell me where I am?" And the guy on the ground says, "Yes, I can. You're at latitude 32.1 degrees south, longitude 101 degrees west, in a hot air balloon 30 meters up in the air." And the guy in the hot air balloon looks down at the guy on the ground and he says, "You must be an architect." And he goes, "Yes, I am. How did you know?" "Well, everything you told me is technically correct, but it's of no use to me whatsoever." There is a comeback for the architect, though. He then looks at the guy on the hot air balloon and says, "Oh, you must be a builder." And he goes, "Yeah, I am. How did you know?" This is where you don't know where you are, you don't know where you're going. You made a promise that you can't meet. You're in exactly the same position you were in before you met me, but now it's my fault. Let's get this show on the road. I've got 25 minutes. I'll do my best not to send you to sleep so that you can be very attentive when Adrian does his presentation. Technology is working. So this is what I want to be talking about. A little bit about climate change. Not that I need to tell Renew members about climate change. I'll talk about the eco-effective design strategies that you can use for a more sustainable home. And then I'll summarize. I can take questions, but then maybe we might leave all the questions at the end after Adrian's presented. We'll kind of play it by ear, see how we go. Oh, microphone. Yeah, okay. This is like, I'm a man. I have to do two things with two different hands. Okay. All right, this is everything you need to know about climate change in only 5 slides. Because we build really bad examples of this, we use too much of that, which then causes too much of this, which then does that, and then does this. Here's a quote, a very brief history lesson. If our designs for private houses are to be correct, we must at the outset take note of the countries and the climates in which they are built. Does anyone know who said that? Famous architect. Not that famous, no, kind of that famous. It was Marcus Vitruvius Pollio, who was a Roman architect. He wrote the oldest work that we have on the Western history of architecture, called the 10 Books of Architecture, and this, I think, was the opening paragraph of chapter 2 or something like that. So a lot of the stuff that Adrian and I will be talking tonight isn't really anything new, and it's not really rocket science. It's just kind of the stuff that we've maybe kind of forgotten along the way, but if we kind of go back to first principles and fundamentals, it can make a big difference to the way our houses perform in terms of their energy consumption and also in terms of their sustainability. So these are the 6 eco-effective design principles that I've kind of come up with over the years that I think cover most of the things that you need to do in order to get a more sustainable, more energy efficient build. Goes something a bit like this. So 1, have to understand the climate and get the orientation right. We need to select appropriate building materials. We need to put in the appropriate windows for both summer and winter. I won't talk too much about windows. That's going to be Adrian's specialty. And then we want to shade the building in summer but allow the sun to enter in winter. We want to encourage air movement and ventilation when it's hot. And then consider energy and water kind of efficient and, I guess, innovative technologies. And I guess that's kind of an order of priority too. I guess depending on the kind of person you are, some people get really excited when they learn about all these new technologies that are becoming available to make houses more energy efficient. Sometimes the best kind of technology is no technology at all. And if you kind of do the first 5 right, then if you've got a bit of leftover money and other things that you want to do to kind of improve and optimize the build, then you can start looking at some of the add-on technologies and the innovative stuff that's available, rather than start with the technology and then kind of forget your first principles. So let's get into number 1, understand the climate and get the orientation right. Here's a map of Australia. This is published by the Australian Building Codes Board and basically identifies the 8 climate zones that we are designing for within the Australian context. Pretty simple. Climate zone 1 is hot and humid. Climate zones 2, 3, and 4 are kind of hot and dry, desert-like climates. Climate zone 5 is where most of the capital cities are located. A little bit hot, a little bit cold. You have to design for both of those conditions. And then climate zones 6, 7, and 8 basically get colder and wetter. Something that I do when I'm designing for a climate that I'm not familiar with is this thing called a building bioclimatic chart. It was invented by a Hungarian architect in the kind of late 50s, early 60s. He was based in the United States. And basically, it's a way of mapping the humidity and the temperature against the different passive design strategies that we can apply to a building. It looks a little bit like this. So that's the chart that Victor Olge came up with. And on that chart, you map the monthly average temperature and humidity, minimums and maximums. And basically, you draw two dots in the chart. You join them with a line, and then that's the monthly kind of trend for that particular period of the year. And then you repeat that another 11 times, and that gives you approximately what kind of climate you're dealing with. Here's basically that building bioclimatic chart for Perth. So you can see in the middle that kind of wibbly-wobbly shape, and if you can just read it, it says comfort zone. So theoretically, when the humidity and the temperature are within that kind of middle kind of blob, then you should be comfortable. If your house is well designed, it shouldn't need artificial heating or cooling in order for you to maintain thermal comfort. As the temperature kind of trends towards the bottom part, that's in red, that's when the building's going to get too cold, and we actually need to heat the building in order to maintain thermal comfort. And for those of you that are familiar with sanctuary and the kind of stuff that we talk about, basically getting the sun into the building and using the sun to heat our building is the most energy efficient and kind of free energy way in which we can heat our homes. And then as the temperature gets hotter, you see we move up into the top part of those other wibbly wobbly shapes, and that's where we're trying to improve the cross ventilation, get more airflow, use thermal mass in order to stabilize the temperature. That's what a building bioclimatic chart kind of tells you about the climate that you're designing for. So I do a lot of work in Perth, so obviously I don't kind of need to look at this on a regular basis. But when I'm designing a building, say in Albany or in a different region that I'm not as familiar with, I'll start with something like this and get an understanding as to which of the design kind of strategies are going to be most appropriate for that climate. Interesting thing to note about this chart is if you look at the number of dots and how they're distributed, a lot of them fall in that bottom half, in that kind of red band, which actually indicates that there's more days of the year in Perth when it's too cold than when it's too hot. And when I said that to clients and people when I do these kind of talks, they go, oh, really? But it was really hot in February. Yeah, it was really hot in February, but it was only really hot in February. Whereas in kind of May, April, June, July, August, it's just a little bit too cold to be comfortable. You probably kind of don't really notice it because it's only a little bit too cold, and it's at 3 o'clock in the morning when you're in bed. But yeah, there's actually more hours and days of the year when it's too cold than when it's too hot in Perth. And once we start understanding the climate and knowing what kind of latitude and orientation we're designing for, that means we know where the sun's coming from, so we can get the orientation right. Here's a very simple kind of extrapolation of a box that's kind of meant to look like a building. That glass you see there is facing north. Down in the bottom left-hand corner, you can just make that out on the compass kind of on the ground. This is what we call a sun path diagram, which tracks the position of the sun at different times and dates of the year. And you do a different sun path diagram for different latitudes and longitudes. And what you can see here is December the 21st. Anyone know what that day is? Summer solstice, longest day of the year. So at 12 o'clock on the summer solstice, the sun is basically directly overhead. And if you look at all that glazing on the north, not very much sun gets in through that glazing because the sun is high and overhead and the building is shading itself through the very shape of its own geometry. As we move through the year, we get to March 21st. Anyone know what that is? Equinox. So the equinox is halfway between the solstices. The sun gets a little bit lower and you start getting more of that solar gain coming into the house, which is just perfect at this time of the year because that's when it's starting to get a little bit colder, and that's when we want to get solar gain inside the house. Then we get to the winter solstice, June 21st. That's when the sun will be at its lowest point. That angle is about 34 degrees at 12 o'clock on the 21st of June, and that's when you're going to get your maximum solar penetration going into the building. So basically the sun is heating your building for free. And then back to September 21st, which is basically the same as March 21st, and then it repeats the following year. And what we're trying to do here is what we call a direct gain passive heating strategy. Basically, the sun is a big burning ball of gas millions of kilometers away in space. It travels through the vacuum of space as shortwave radiation. Some of it passes through the Earth's atmosphere, some of it gets diffracted by clouds. When it hits the glazing of your building, that shortwave radiation turns into long-wave radiation. Long-wave radiation is basically infrared, so then that starts to heat up the space. That long-wave radiation can't pass back out through the glass, and that gives us our direct gain passive heating. I just want to show you an example of a building that I used to live across the road from in Leederville, where they thought about the orientation, but they didn't quite get it right. So this is on Loftus Street. I used to live across the road. They knocked down one of those houses that Adrian's currently renovating. And they built these series of townhouses here, and you can see that they've got a balcony and a living space upstairs above the garage. Hard to tell from this photo, but all of those living spaces and balconies are facing south, which, if you've heard anything that I've said in the last 3 minutes, is the exact opposite of what I've been talking about. Why did they face that south? Well, that's because they wanted to take advantage of this very lovely view of the Perth city skyline that you get from that particular part of Leederville. Unfortunately, they get a view a bit more like this. Because about 2 years after those houses were built, they built more townhouses on the south side of the block, but they built them 3 stories high. And the interesting thing is they then faced all of their windows south and did exactly the same thing. And you see that kind of little window there in the top left-hand corner of each of those townhouses? That's the toilet, and I think the one next to it is the bathroom. So they didn't really think about the orientation. And a couple of years ago, again, they've built more 3-story townhouses to the south of that one, and all of that lovely south-facing view is gone. Interesting thing about our planning policies in Western Australia, there's nothing in the planning guidelines that will protect your right to a view. However, there are policies that will protect your right to have access to the sun. So it pays to actually take advantage of the sun in any way, which way you can. Which brings us to building materials, and then I'll talk a bit more about insulation. Basically, when you look at the way heat flows in and out of a building, if you break it down by percentage, these are very rough kind of percentages, but if you add up the floors, walls, and roofs, about 3/4 of your heat gain and heat loss occur through the building fabric, the building envelope. So it's really important that we choose the most appropriate materials to build our building out of in order to minimize the heat flow in summer and in winter. Part of that is installing this lovely stuff here called insulation, and it's basically the easiest way in which you can improve the thermal performance of a house. This is batt insulation being installed in a timber-framed wall. There are many different types of insulation. And just to give you a little picture as to how that works, here's a graph of a building that has no insulation, and you can see the different months of the year along the bottom and the 24 hours of the day on the vertical axis, and it shows you the heat flow that occurs at different times and dates of the year. So green means that there's not very much heat flow happening. Red and orange mean there's lots of heat flow going into the building, as you can see in summer, and then when it goes blue, that's when the heat's flowing out of the building. That's a building with no insulation. This is a building that has insulation, using the same scale on the graph. So you can see that it dramatically reduces the heat flow that occurs. Kind of makes sense. There are 2 different types of insulation, and these are technical terms. Basically, there's the fluffy stuff and the shiny stuff. The fluffy stuff is also known as bulk insulation, and that's stuff like glass wool, polyester, rock wool, or blow-in insulation. That works really well in winter. The thing to remember is that that insulation doesn't work if you squeeze the insulation down to fit. So if you've got a wall that's 100 millimeters thick, but your insulation batt's 150, you can't go, oh, we'll just kind of squeeze more insulation in there, and therefore the building's going to perform better. When you squeeze all the air out, the insulation actually stops working, and then the heat flow actually occurs through the insulation material itself. It's the air that's trapped in the bulk insulation that makes it effective as an insulator. And then there's the shiny stuff, and it goes by all kinds of names: sarking, foil, double cell, anti-condensation blankets. This is really good for reflecting heat gain or heat loss via radiation, so it works really well in summer. However, the shiny stuff doesn't do its job properly unless there's a gap of air next to the side that's designed to reflect that radiation. So you don't want that to get dusty, and you don't want to sandwich it between 2 materials and have no gap whatsoever, because otherwise the shiny stuff doesn't work. A couple of useful things to know about insulation. So we measure it using this thing called the R value, or the resistance value, and basically the higher that number, the more resistant it is to heat flow. These are the recommended R values for your different types of construction. So if you have a floor above ground, you'll need an R value of at least 1, sometimes higher. Walls somewhere between 2.4 to 2.8, and then you've got roofs and ceilings at 4.1 to 5.1. You need more insulation in the roof and the ceiling, because that's obviously the surface that gets exposed to the most amount of heat gain and heat loss, both in summer and winter. The thing with insulation is that the more insulation you put in, yes, that increases the R value, but it's not a linear relationship. So if you put in twice as much insulation, you don't get twice the R value. It's actually a slightly diminishing return. So it's about kind of optimizing the thickness of your wall so that your walls don't end up being too chunky, while also getting a good kind of level of insulation. Insulation needs to meet the following Australian standards. So there's AS 4859, which describes the materials that you can use for insulation, what goes into it, whether it needs to be fire retardant, all of that kind of very important stuff. And then there's also AS 3999, which describes how the insulation has to be installed. If the insulation isn't installed correctly, it's not going to be able to do its job. Here's an example of one that I prepared earlier. This is an example of a kind of bulk insulation, but this is a rigid board insulation. So basically this is polystyrene. Oh, hello, lights. Maybe if I hand that to this gentleman here, you can kind of pass that around, try not to whack anyone in the head with it. Doesn't hurt though, it's all right. That's one example of bulk insulation. You're starting to see more of this kind of stuff being used in buildings. It can provide a very high level of insulation. So the advantage to an insulation like that is, as you can see, it's very light. It's easy to hand around, to kind of throw into a crowd and go crowd surfing. The R value for that, I think, is about R2.5. So it's a relatively thin material that has a very high R value. Whereas if you do your kind of fluffy bulk insulations, they tend to be thicker in order to achieve the equivalent R value. But you have to be careful because, one, it's made from petrochemicals. So for those of you that are trying to be a bit more holistic with your sustainable building approach, you need to think about where the chemicals and materials are actually coming from. And if you don't install it properly, it can be a fire risk. So you have to be a bit careful there. I don't have an example of a reflective foil, unfortunately. There is a particular insulation that's available that gets a lot of recognition. It starts with air and ends with cell. It's a good insulation, don't get me wrong. However, you'll find that it performs really well in summer, but not so well in winter. So some people kind of, when they spruik this particular style of insulation, it's not necessarily just this company, they'll say, oh, this is the only insulation that you need to install. However, in my experience, it works really well in summer, but it doesn't work so well in winter. And given that there's quite a number of cold days you have to design for, you need to make sure that you're covering kind of both kind of temperature extremes. And then there are bulk insulations that are made from natural products such as wool, and also kind of natural fibers, and also ones that contain recycled content. So there's one insulation that I use a lot of that actually is made from recycled glass bottles, where they take the glass bottles and they kind of respin them in order to make the glass fiber. It's low allergy, it's hyperallergenic, so it doesn't cause skin irritation like some glass fiber insulations do. So a bit of research to do there in terms of the many different types of insulation products, but make sure they comply with the Australian standards, make sure it's being installed correctly, and then I guess you need to weigh up the thickness with the performance and some of the other criteria that you might consider. Going to talk about thermal mass. So basically thermal mass is anything like me, heavy and dense. If you add thermal mass into a building, such as with concrete or with brick, that helps to regulate and stabilize the internal temperature inside your building. So if we elaborate on that diagram that you saw in the previous slide, the sun's coming in, heating up the space, so that's direct gain. But then some of that heat energy is actually getting absorbed by the thermal mass that's inside our building. So imagine that's a polished concrete floor. Some of that solar energy is going to get absorbed into the thermal mass of the floor. When the sun goes down, there's a temperature difference now, and basically that thermal mass has thermal capacity. It then releases that heat and actually continues heating your building even though the sun's gone down. So that's an indirect kind of gain strategy. And it also works in summer because it helps to regulate and keep the temperature more stable inside your building. Quick graph to show you how thermal mass works. This is a graph of the hottest day of the year in Perth, which statistically is February the 4th. The blue dashed line is showing you how the temperature is changing from night through to day. And then we've got a brown kind of line there, which is the temperature inside a room that has no thermal mass. And you see basically when it gets hot outside, it gets hot inside your building. If we change nothing else but add some thermal mass, it will look something a little bit more like this. So you get a more stable temperature. It doesn't kind of peak as much as it does in the middle of the day, and it helps to kind of keep that temperature at a more kind of comfortable level. We need to think about color as well when we talk about building materials. So basically, it's a bit like a car. The color of the car will affect how much solar radiation it absorbs. Here we've got the standard ColourBond colors. It's a property known as a solar absorptance, which is a number between 0 and 1. And basically, if you have a number like 0.7, if you look down at the bottom there, deep ocean, 0.74975, that means if 100% solar radiation hits that surface, 75% of it gets absorbed, 25% gets reflected. Which is why most of the buildings I design have a surf mist roof, which is 0.318. So 69% of that solar radiation gets reflected, and only 31% of that gets absorbed. You can also get heat reflective paints and coatings. Bear in mind, they only work if they're kept clean and dust-free. Just to show you a little bit more, as I said, I'm a bit of a weird architect. I like spreadsheets and graphs. Here's a picture of the heating and cooling loads in a building across the year if it has a dark colored roof. And you can see basically the blue bar going down below 0 is when you're taking heat out of the energy, heat energy out of the building because it's too hot. And then the red bar is when you're adding heat into the building in order to make it warmer because it's too cold. That's if it's got a dark colored roof. If we change it to a light colored roof, you can see that it dramatically reduces the amount of energy that you have to take out of the building. So changing the color of your roofing material doesn't usually change the cost of your building, but it will make a dramatic improvement to the performance of your building. And if you have air conditioning in your building, the air conditioning doesn't have to work as hard because it doesn't have to remove as much heat energy from the building. The more astute of you may have noticed that because we've gone from a light colored roof to a dark colored roof, that actually increases the amount of energy that you need in winter for heating because it's reflecting more heat. However, the net gain for the heat that you don't get now because it's a light colored roof compared to a dark colored roof, that more than offsets the winter detrimental performance. So it's much better in summer for a small detriment in performance in winter. So just to summarize building materials, when you're selecting them, you're trying to use a combination of the shiny stuff and the fluffy stuff in order to insulate your building to cater for both summer and winter conditions. You want to incorporate thermal mass in the floor and keep that thermal mass exposed. Like we do a lot of buildings with concrete slab on ground, which is great for thermal mass, but then if you cover it with carpet or you cover it with wooden floorboards, that thermal mass is then insulated, so it can't actually work to its optimum advantage. You might want to consider a material which has thermal mass on the inside and insulation on the outside. And you may be familiar with this way of building a wall called reverse brick veneer. I have 2 clients in the room that are very familiar with it, and I didn't do a very good job of explaining to them that I wasn't designing a reverse brick veneer house for them. But they've been very, very accommodating, so thank you. Basically, that means putting brick on the inside, a frame on the outside, insulate the frame, and then the thermal mass regulates the internal temperature, does that lovely solar gain thing, and then the insulation on the outside protects it from the extreme temperature on the outside. And that allows you to optimize the performance of your building. Light-colored materials on the outside work best, and then you might consider heat-reflective paints for your roof. Just a really little simple tip. Basically, builders have been building cavity brick houses in Perth since the dawn of time, and it's what they've always done, and why do we need to change anything? Because that's the way it's always been, and everything's fine, and why do we need to do things different now? Basically, some rather kind of naughty people have found a loophole in our energy efficiency requirements under the building code that allows them to build houses that don't have insulation in that brick wall cavity. I can tell you now that they're kind of rorting the numbers in order to make it look like the building still meets the energy efficiency requirements when it doesn't. And I've actually seen, I've been giving design advice to a couple of friends that were building, and you look at the specification they get from the builder, and it's got no wall insulation specified at all. And basically, that particular builder is doing something dodgy. So if you're thinking of looking at a builder, make sure they put insulation in the walls. Anyone that tells you they don't have to means they're doing something wrong. Okay, I'm not going to talk too much about windows because that's Adrian, but basically windows are a very important part of the building. There's 3 ways which heat transfers through a window: radiation, convection, and conduction. It therefore means that windows and the way you select and specify your windows is critical to the performance of your building because there's so many different ways heat can flow in and out of those windows. Sometimes you want the heat to flow through the window to heat your building. A lot of the times you don't want that heat to flow back out because you're trying to keep the warmth inside the building. And sometimes you're trying to keep the heat out. Just a little picture to kind of show you what a building looks like. This is a model of a room that has a standard residential aluminium frame, which is what most builders use in Perth. It's not a particularly well-performing window. There's a technical term for it. It's shit. And if you look at that graph, that grid across the floor, that shows you what the temperature's like inside that room on a cold winter's night. So if you're standing next to that window, you can see it's actually colder in that part of the room compared to the rest of the room. And if any of you have been in an old building with crappy windows, you actually feel it sucking the warmth out of your body. If we just put in a better quality window, double glaze, better frame, that kind of stuff, you see not only does the temperature increase a few degrees, it actually becomes a more stable temperature. So just by tweaking the windows, you can make a big difference to the performance of your building. It's also the bit that can get very expensive, as I'm sure Adrian will talk more about. So it's about selecting the best quality windows for your budget, not making them too big, putting them where they need to be. All of those things can really influence the performance of your building. I'm going a little bit over time. Is that all right? Okay. I don't want to steal your thunder, Adrian. Okay. So now we move on to shading. And we're trying to keep the sun out of the building in summer, but we want that sun to enter the building in winter. And really, the simplest way to do that is to put a hat on our building. So just like how we have to put hats on when we go out in the playground these days, you want to do exactly the same thing with your building. So here's that box that I had before. I put a standard roof on it. This is how a lot of kind of builders build houses these days. It's an interesting architectural style. It's part Federation, it's part Mediterranean. I like to call it Fediterranean. And this is basically because they've got houses they're trying to build to have bigger floor areas, but the lots are getting smaller and smaller. So what they do is this thing where they box out the eaves and actually build what used to be the eaves, the outside overhang when you're building, they build it into the building itself. And then you end up with something that looks a bit like this. It doesn't cost any more to put eaves in a building, but see what difference it makes with the shading. So all four walls of that building are now shaded in the middle of the year in summer. And that dramatically reduces the amount of solar radiation that hits the building and then has an adverse impact on the temperature inside. Lots of other ways in which you can shade a building too. You can put louvers, screens, timber slatting, awnings, you name it. But the eaves is the easiest way. It doesn't really cost anything to do it. But I'm an architect and I design buildings without eaves too because they look cool. So it's about balancing and understanding the impact that has on the performance of the building. Okay, second last eco-design principle, and that is encouraging air movement and ventilation when it's hot. And basically we want to get air flowing through the building because it's basically free air conditioning. We don't have to use mechanical cooling in order to cool down the building. Now, windows have all these different kind of opening types. There's the sliding window, casement window, louver window, and they've all got different percentages of opening, which basically reflects how much air can move in and out of those windows. We used to use a lot of sliding windows, which provide a decent amount of ventilation. What you're seeing more and more of are these windows here on the far end called awning windows. And basically they're hinged at the top, they only open at the bottom, and you can do kind of big bits of glass with them, and they're pretty cheap and easy to install, and builders love them, but they're actually not very good from a ventilation point of view. Because basically, because it's only opened at the bottom, when the wind comes along and hits that glass, it doesn't go through the window, it actually deflects up and goes away from your window, and very minimal kind of comes underneath. Because when the wind hits the glass, it doesn't go, oh, wait, it's an awning window, I'm going to need to go underneath here and then kind of ventilate the room this way. It basically just gets deflected from your building. The other reason why awning windows get used a lot is because we don't want little kids falling out of windows, because that's a bad thing. So on upper story, two-story buildings, we put these windows in with a restricted opening at the bottom to stop kids from falling out. Which is a legal requirement. And I don't mean to make fun of the fact that kids shouldn't fall out of windows, but there are other ways in which you can make windows ventilate well and also be safe and make sure kids don't fall out of them. So awning windows can be used in some circumstances, but they're not really the best window for ventilation purposes, in my humble opinion. Adding ceiling fans is always a good thing too. We're at home base. I do believe big ass fans have got a display downstairs. There's a funny story about why they're called big ass fans. I can tell you later during the break. But basically, ceiling fans are a very economical and very cost-effective way to cool a room or a space. I do believe the statistics are that if you have a ceiling fan in a room turning on a hot day, you will feel something like 5 degrees cooler, possibly even up to 10 degrees cooler, just because of the air that circulates and increases the rate of evaporation from your skin. And then what we're trying to do with ventilation is to use it with that thermal mass design strategy that I talked about under building materials. Thermal mass traps and retains heat, which is good in winter, but can be a bit of a disadvantage in summer. And that's the problem we have with a lot of houses in Perth, because we build concrete slab on ground, cavity brick, lots of thermal mass, but then we close up the house during the day in summer, then we get home and go, oh, gee, it's hot in here. Then we turn the air conditioning on for the next 18 hours in order to cool our building down. Whereas what you want to do is have windows that you can open, catch that lovely southwesterly free old doctor breeze, and flush that hot air out. It resets the thermal mass, and then the next day comes, and then it can start absorbing and regulating that temperature again. So that's called night purge ventilation of thermal mass. It works with your thermal mass in your building. Draft proofing your building, making sure you don't have any drafts or leaks in the building. That basically stops air from transferring heat into and out of your building. You tend to notice the effect of this more in winter rather than in summer, but also in summer, if your building's not airtight, then heat's getting into your building and causing it to warm up unnecessarily. Okay, and that brings us to the last section, which is consider energy and water efficient technologies. I'll fly through this because a lot of you will know this being Renew members. Solar PV, it's a no-brainer. Basically, you'll get a payback within 5 years, generally speaking. So that's a really smart and easy thing to do. Lots of people that know more about solar PV that I can tell you more. Looking at the way you heat your water, that's another big user of energy inside buildings. So you might want to look at solar hot water, heat pumps. All of those will help to reduce your carbon and energy footprint. Knowing how you're using your energy is kind of the first step in order to optimize and improve your energy efficiency. So nowadays you can get these energy monitoring programs on your iPad and on your phone. I can turn the lights on in my apartment from my phone these days. If you understand where the energy is being used, then you know where it is that you can optimize and save. Light switches are a good idea because they let you turn your lights on and off. The reason I put this light switch in my apartment, I've got a switch by my front door, which is a master switch. So when I flick that and go out, it turns off all the lights in my house. So I don't have to go through and turn off all the lights. And if you live in a bigger house, that's a really easy thing for an electrician to wire in for you. It costs a couple $100, and you can basically minimize your energy use through a very simple wiring configuration. Energy efficient lighting, LEDs. Basically, I think all lighting these days is some form of LED. The thing to remember is that heat is what destroys an LED. So you need to make sure that it's ventilated properly. As an architect, we like to do a lot of recessed downlights. The problem with recessed downlights is, though, that then creates a hole in your ceiling. And that hole means you can't really insulate all the way around that. And then the air kind of escapes through it and makes our building less energy efficient. You can get downlights now that are specially designed for fire safety, where you can run the insulation over the top of the downlights. So you want to look for those when you're choosing and specifying your lighting. And then the way we use water, shower head, obviously when we take showers, 4-minute showers, all that kind of stuff. But you can also get some very water efficient shower heads that are available these days. This one uses about 5.5 litres per minute compared to a standard shower, which is about 7 to 9 litres per minute. And then I'm sure you've seen toilets like this. I have one in my second bathroom, where basically you can do your business, and then when you flush, the water that comes through the tap fills the cistern, you wash your hands, and then that is what's stored for the next flush. Just to be clear, you're not washing your hands with dirty toilet water. And everyone loves electric vehicles, and that's probably going to become the norm in the next kind of 10 years or so. I don't really need to tell you any more about that. So that summarizes the 6 eco-effective design principles. I do believe you can get a copy of the presentation. So yeah, hopefully there's something useful in that. I've got one more slide. Here's some free stuff, some stuff you already know about. The Your Home Technical Manual, brilliant. Australian government initiative, basically lots of information and technical data on how to design a more sustainable, kind of waste-free home, and all the things you can do to make it a better place to live. Except it's not called the Alternative Technology Association anymore. The Sunulator and the Tankulator are 2 tools that you can find on the Renew website. One helps you to calculate the size of your solar PV, what kind of payback you're going to get, how much energy you're going to generate. The other one can be used to work out the sizing of your water tank to make sure that you capture and use the most amount of rainwater. NatHERS is the scheme we use for assessing the energy or star rating of a home. You can do a similar thing for Windows. 2 links there that have more information about insulation, because I was asked to focus on that. That last one's particularly good. It's done by the Master Builders Association, where they actually have a video to show installers how to check that the insulation has been installed properly. So really good to see initiatives like that coming out of industry. That's it. I'm done. I went 10 minutes over. Sorry.
Okay. All right. So, why should we build energy efficient homes? Actually, I'll click because I'll flick through them pretty quickly. Yeah. So there's a variety of different reasons, and obviously environmental reasons. Climate change is a big one, we all know, so we should be doing it for the climate. The National Construction Code tells us that we need to meet a 6-star rating. I've got a big B in my bonnet about 6-star rating. I think it goes anywhere near far enough to what we need to do, and it's an average, and it's pretty useless really. But anyway, we need to comply with it. Mandatory disclosure. So mandatory disclosure is something that's been supposed to have been coming in for a very long time, and it means that when you go to sell your house, you have to have your house assessed and it'll get a star rating. Okay. We have to do it for commercial buildings, but for residential, we don't have to do it yet. Something to consider. Maybe one day it might come in. This is the key one for me. If you design an energy efficient home for yourself, you'll get the benefit from it. Everyone gets the benefit from it. So you don't need to go over the top. You just need to think about what you need for yourself. So if I go back to about 15 years ago, we were designing a rammed earth house up in the hills for a client, and they wanted to achieve an 8-star rating, which was pushing. I think it was only maybe 4 or 5-star back then. So we were going a long way past the minimum standard. Now, they had views to the south. They were using rammed earth, which doesn't perform very well unless you insulate it. Everything was wrong about this house in terms of doing an energy efficient house. during conversation, we were putting double glazing and all sorts of things into this house to make it perform, and the cost was going up and up and up. Then one day, they said something about they're loving the outdoors. And I said, well, what's that mean? So, well, when it's cold, yeah, we open doors and windows. We love the cold. What about when it's hot? Yeah, we just open doors and windows. So what are we putting all this expensive double glazing and on all these other things into your house when your lifestyle doesn't dictate that that's the way you're going to operate in this house? So we didn't design their house with double glazing. We just made sure we had good ventilation. We made sure that we got winter sunlight in where we could. Every year when I go back there, their energy bills are almost nothing. They've got some solar PV on the roof, only about 4 kilowatts, and they're energy neutral. So it's really important, I think, that when you're dealing with your designers and your architects, that you really express how you want to live in the house. Because passive house works great for some people, but it only works if you're going to keep your house locked up at the right times of the year. So, and then using thermal mass will work for some people, but won't work for other people as well. So totally changed the way that we started designing at ecohabit, and we really think about what our client's lifestyle is and design for the individual. Okay, so how do we assess a home? Sid touched on this a little bit. You've got this climate map, and down in Perth we're in climate zone 5. Now, if you're up in Broome, you'd be climate zone 1. Climate zone 1 is generally a hot climate. It's pretty easy to contend with a single type of climate zone like that. You make sure you deal with ventilation, you make sure you keep the heat out. It's pretty simple, really. When you come down into Perth, we've got a pretty severe winter, we've got a pretty hot summer, so we can get 40, 45 degree summer days, and we can get down to 1s and 2s in winter sometimes as well. So it's really important that we deal for both of those climate conditions. When you go along to a builder typically, or a lot of designers, the way they assess your home, they'll assess against the National Construction Code for the 6-star rating. It's a blanket approach. If you could have a room, your living rooms could be performing at 2-star. Your bedrooms are all performing at 8-star. Your average is above 6-star, but the space that you spend most of your time in your living areas is poorly performing. So the National Construction Code falls well short. When we assess a home, we've got a totally different approach. So when we send our design off to an assessor, the assessor that we use, we stipulate glazing, frame types, etc., wall types, so on. Then they come back with this graph. And we can see each individual room. We can see the star rating of each of those individual rooms. We can see that the study is only a 2.7 right down the bottom right there. Right in the middle there, bedroom 3 is performing pretty well, and so is bedroom 2 at 8.1. But the more important things are the heating and cooling loads. We can see exactly what those rooms, how those rooms are performing. And we can say, well, we know that bedroom 3 and 2 are perfect. Why is the study not performing? And generally, it's a glazing issue. 9 times out of 10, it's a glazing issue. Windows pointing the wrong way or something like that. It's not shaded properly. So controlling heat loss and heat gain. So a little bit of science here. And I'll try and whiz through this and try and keep you awake. I've got no jokes, so I'm not as funny as Sid, so hopefully we can keep you going. So heat transfer. As Sid pointed out, conduction. Conduction happens in solids. It's the vibrating of atoms through a solid. Heat transfers through the solid in that manner. Convection happens in liquids and gases, caused by the movement due to a substance becoming buoyant. And then you've got radiation, and Sid talked about radiation, how radiation works from the sun. So, a couple of facts. Heat transfer happens when there is a temperature differential from inside the building to outside the building. Nice and warm in here, it's cold outside, single glass here, all the heat's escaping out through that window. The rate of heat transfer is very much dependent on the conductivity of the structure itself and the temperature differential. Air is a bad conductor of heat, thus provides good insulation. If you remember anything from that slide, that lifeline is the most important one. So Sid touched on R values as well. Now, an R value is the ratio of temperature difference across the material. So K is a conduction coefficient, that's a standard. D is the thickness of the material. D divided by the coefficient for that particular material will give you the R value. So down the bottom there, higher the R value, better the insulation, slower the heat transfer. Again, just remember that line. So this is a standard graph, and if you Google insulation graphs and tables, all this sort of stuff comes up. There's heaps of it. So fiberglass bats, gives you an R value of 3.1, 4.3. Snow, if you could hold it cold, gives you an R value of 1. Brick gives you an R value of 0.2. Glass, 0.14. So your brick is performing, a single leaf of brick is only performing slightly better than a single pane of glass. The only reason double brick even comes close to being a performance wall system is because of the insulation, the air cavity in the middle. The problem with that is that we go connect the leaves of brickwork with metal wire ties which conduct heat and energy. So, not a good system. Then if we start, now we're starting to move on to glass. So U values describes how well a building element conducts heat. Okay, so it's the inverse to R value, where K is, again, the coefficient for that material, and L is the thickness of the material. Now, smaller the U value, the better at reducing heat transfer. Okay. So if we go down to the bottom there, we look at a single pane of glass, 1.2, and then a double pane of glass, 0.7. So we're looking for low numbers. When we're talking about glazing and U values, we're looking for low numbers. So controlling heat loss and heat gain. So we need to focus on the weakest link. So when we think of a building fabric, think of an esky. Okay, esky kind of follows passive house principles. You've got an internal skin, you've got an external skin, and you've got an insulator in between, and you've got no thermal break in between it. But we need to get into that esky, so we stick a door in it. Then we want a bit of sunlight into it, so we stick some windows in it. So we create a leak in our building. We create a hole in our building where heat can come in and out of the building. Then we go and stick any thermal. A lot of the times when we look at homes, and Sid will attest to this, you look in the newspaper and you'll see a home that's supposed to be solar passive design, and they've got this great living area with some beautiful glazing, and then they stick an al fresco roof over it, and there's no winter sunlight comes into it. So it's kind of what we're doing here. So weakest link is glazing. So Sid's touched on this, conduction and radiation. There's a couple of other things to consider with glazing as well. So we've got convection. So that happens when warm air comes in contact with a cold element. So if you've got single glazing and you're trying to heat up a room and the warm air touches that glass, it cools rapidly and it drops. So if you've ever sat in a room that's actually pretty well sealed up and pretty airtight, and you feel a draft and you're going, where's that draft coming from? And you're sticking towels in your door and you still feel it. Quite possibly it's the warm air touching the glass and dropping and creating that convection current. Air leakage is another thing to consider as well. So we focus on conduction and radiation here. So we talked about U values before. The lower the number, the better at reducing heat transfer. The other thing you've probably heard of before is solar heat gain coefficient. So that is the proportion of total solar radiation that is transferred through the glass at normal incidence. Again, remember the last line, lower the number, the better the solar performance. So when we talk about insulation, we want big numbers. R4, R5, great. Windows, U values, solar heat gain, little numbers. So if we look at this graph, which talks about the different types of glazing, the first line up the top, right up here, we're talking about clear 6mm thick glass. We've got a U value of 5.8. If we move down to the, and a solar heat gain coefficient of 0.82. We move down to the grey glass, and we can see that the U value drops to 3.6, but the solar heat gain coefficient drops quite dramatically. If we focus on the U value for a moment, from a single pane of glass, we're at 5.8. Now, if we come right down to the bottom here, we've got double glazing. So 6mm glass, 12mm air cavity, 6mm glass. 2.7. So from 5.8 down to 2.7. So we've dramatically improved the efficiency of that glass. Now, solar heat gain coefficient, double glazing, but clear glass. So the solar heat gain coefficient is only 0.71. The grey glass, 0.39. So what the grey glass is, it's an impregnated glass, or have some sort of film on it, or something impregnated the glass that will reduce the radiation. So when we talk about locating our glass on our building, these days I push for double glazing throughout the whole building. I think it's a no-brainer. If you're going to spend any money anywhere on your house, you spend it on your glazing, you put double glazing in. There's not a house that I've done in the last 4 or 5 years where we haven't double glazed it. So it can be affordable. When you talk about construction costs and how much a home costs, there's several different factors that you look at. You look at how big the house is, you look at the quality of the finishes, and you look at the structure. Now, if you find that, and I put glazing into the structural element of that. Now, if you're finding that that the structure, the overall budget is too high, what we generally look at reducing the size of the footprint of the home before we start looking at reducing things like double glazing. Double glazing for us now is the last thing that we pull out of a home. Grey glass and glass that you're using to stop radiation, the only time that you really need to do that is when you've got a window that's been put in the wrong place in your house, in my view. So if you've got an east-facing window or a west-facing window, that's when you need to try and keep that radiation out. If the house is designed well, you should never be needing to put it on the northern side of the house, because you actually want to be getting radiation in. You want to be getting that heat down onto your concrete slab and warming it up. So window frames. There's lots of different types of window frames out there. Single glazed aluminium window frame is probably the standard. That's the one that we've all seen. It doesn't perform that well. Our office in Northbridge, which we didn't design, we're on the top floor. We've got glass on a northeasterly direction, and we've got an eave which is probably about 600 wide. We've got a wing wall that actually protects that glass from the east. So in summer, the sun actually doesn't really touch our glass and actually performs pretty well. In March through to even this time of year, we're actually starting to run our air conditioning harder now than what we did in summer. It just sounds absolutely ridiculous because the sun is coming directly into our glass and it's heating up so dramatically. And to give you an idea how much of an impact it's actually having on the building, I did a little experiment and I put some thermostats outside and inside the building. There's a 16-degree day, sunny day, and 16 degrees, that's measured by the Bureau of Meteorology in one of their shaded boxes. I can't remember the name. What they call it? Anyway, that's it. So 16-degree day. On our balcony in the sunshine, it's 24 degrees. Inside the glass, it was 32 degrees. So that's the power of the sun. It's pretty incredible. Okay. So putting your glass in the wrong place in your home is the most detrimental thing that you could ever do. And we've got Comfort Plus glass, so it's got the radiation film on it. There's nothing we can do to stop that heat coming through except to probably put louvers in the front of it or maybe a big awning structure or something like that. The only other thing we can do is run our air conditioning because everyone's getting hot. It's crazy. Timber frames. Timber's pretty good. It's not the perfect insulator, but it's certainly better than a aluminium frame that's not thermally broken. And if you double glaze a timber frame, it's not a bad system. And the quality of timber frames that you get these days, they steel up pretty good. So we have put them in some of the houses that we design. Aluminium thermally broken window frames, are certainly near the top of the list, along with UPVC. So undoubtedly, these are the two systems that you should be looking at. Now, I love to promote local products, but I've got to say that we can import thermally broken aluminium double glazed window frames for the same price you can get unbroken aluminium window frames. The amount of heat transfer you get through a window frame is quite incredible. So double glazing and not having a thermally broken frame or a UPVC frame is probably only going halfway there. Now, I'm renovating my own house at the moment. This is a bit of a real dilemma for me because we're renovating, we're going to hit a point. We can't order windows until we've got some structure in place that they can actually site measure. If you're building new, it's okay because they build the walls in around the frames. But renovating, the openings need to be site measured. So from the time that we get those openings prepped to the time we can get some windows in, if we look at overseas, we're looking at 12 weeks. If we look locally, we're looking at 3 weeks. So we either have a 12-week delay to our program of our project, or we use local product. Now, local thermally broken frames on my house are going to cost about $80,000 locally. Unbroken frames here, $35,000. Thermally broken frames from overseas, about $32,000. And these are all installed prices. So, you know, and UPVC was somewhere around about that 35 grand mark as well. And the UPVC ones that, a lot of them, some local ones now are actually pretty good and pretty affordable. So, yeah, so there's a bit of a dilemma there in what we are going to do, but you know, there's a lot more choice out there now, and if you're going down this journey of building a new home or renovating, look at all the options out there. There's quite a wider range to view. So window styles, and Sid kind of touched on this as well. So sliding windows, in my mind, yeah, okay, but only half that window's an opening window, so you're not getting the best out of that window in terms of crossflow ventilation. Louvers, yep, fantastic for ventilation, but you can't seal them. Now, some companies are coming out with double glazed louvers. I still don't know how well they will seal, and they certainly won't be as good as a normal double glazed window. Maybe it's an option, I'm not sure. I do love louvers. I grew up living in Narrogin in a sleep out with a louvered sleep out and freezing cold, and you know, rattly louvers, and that's kind of fun, but you know, probably not the best thing for a performance building. Awning windows. Now, the National Construction Code says that when you calculate the airflow of an awning window, it's that whole area, which I don't get because it only opens this far. But anyway, another flaw in the construction code. They're okay. Double hung windows. We're putting more and more double hung windows into homes now because you can, as you slide them up and down, you get an opening at the bottom, an opening at the top. Helps with crossflow ventilation and circulation through the house. It's kind of cool. But for my mind, casement windows are a no-brainer. As Sid was pointing out as well, a casement window, you can open it up to 90 degrees. You can maximise the ventilation. You can have a whole bank of casement windows, and the whole wall can open up. But the really cool thing that I love about casement windows so if I draw a corner of a room, and let's say I pop a window in here. This is my casement window. So this is a plan view of a room. It's opening up that way. When the wind blows across the face of that window, creates a low pressure, sucks great volumes of air out of your house. So a lot of airflow will happen through suction, principle called the Bernoulli principle. Google it, look it up. So air passing an opening. It's like that old trick when you get a straw, blow across the top of the straw, and you stick a piece of paper on the bottom of it. It lifts the piece of paper up. It's the way an aeroplane wing works. Airflow across the aeroplane wing creates a low pressure. Aeroplane lifts up. So it's a very powerful principle to use in designing of windows. if you look in if you Google Bernoulli principle, maybe Google Bernoulli principle houses, then you'll see a lot of this sort of stuff. In Europe, they use chimneys on buildings, so airflow coming across the top of the chimney creates a Bernoulli principle, sucks great volumes of air out of the house. So casement windows, in my mind, if you orientate them the right way and you orientate them with the back to the prevailing wind, you'll get far more airflow through your house than any other type of window. There's a couple of different systems for holding casement windows open. You've got like this one on the left, which is a lever system, so you give that 90-degree angle. The other system is like what you do with an awning window, the winder. Unfortunately, the winder systems, you don't get much of an opening, so they'll be restricted to maybe a few hundred millimetres. The European-style tilt and turn windows, we do some passive house designs, so the tilt and turn windows are making their way into our homes more and more often these days. The one thing I'll say about tilt and turn windows is be really careful. They open inwards. Be really careful where you put them, because if they do open inwards, and if you're thinking about putting a dress there or something like that, you might not be able to open it. We've been caught out a few times where we've designed the windows to the way that we thought, and we thought we really explained it to our clients. This is the way your window's opening, and for some reason they didn't quite understand. And when the house was built and they went to open their window, they were going, "Oh, I don't wanted to put a something or other there," and the window's going to get in the way. So just be aware that they do open inwards. The tilt and turn, you can open them from the top, close it, open them like a casement inwards. So pretty cool. Fly screens. Now this is a real dilemma, because when you put a fly screen on a window, you reduce airflow by maybe up to 50%, depending on the screen. The same with security screens. So you spend all this money having great big casement windows or whatever else to get good crossflow ventilation, and then as soon as you stick a screen on it, fly screen or a security screen, you might actually lose a lot of that benefit. So just think about that. Also, how are you going to open your windows? So if you do use a casement or an awning window, awning, bottom left there, so you've got the winder. But if you use a casement window with the mechanism I showed before, well, that's not going to work because your fly screen's on the inside and you're not going to be able to get to the handle and open it up. So there's some challenges there with that. The tilt and turn windows, that's probably one of the benefits of them, because you can put a security screen on the outside, because they open windwards. Perfect. Of course, you've got different types of fly screens. You've got these magnetic ones that you can pull off, and you've got the retractable ones. So there's a whole lot of different ones that you can utilise. So that's kind of it for me. So I flipped through that pretty quickly, but I certainly got lots to say. So if you've got questions, I'm more than happy to continue answering. Those 3 points at the bottom there, when you're looking at glazing, little numbers, the most important thing. The little you can get those numbers, the better the outcome. But really talk to your designers, push your architects, push your builders to assess your building properly and assess what's happening with the windows, so you can get the best out of your windows in terms of efficiency, whether it's to do with sunlight, whether it's to do with keeping heat in, or whether it's to crossflow ventilation. I'll just touch on one quick little thing. We've got 1 more minute. When we were talking about, Sid was talking about solar passive design and thermal mass, and I'm thinking a little bit differently these days. And it's not about, both are right, but I'm wondering if the future of housing, with the advancement of solar PV, battery technology, high efficient materials, whether we're moving to a direction where we build homes a little bit more like an esky. It doesn't mean we have to use it like an esky, build it like an esky. Putting solar PV on the roof, we're storing our own energy. We can heat our homes, cool them all day long, and it's all free from the sun. In my own home, I'm thinking about electric underfloor heating with a concrete slab. I'm thinking, maybe we can heat that slab all day for free, turn it off, and we're using that thermal mass, and that heat's coming back out of our slab all night long and stabilising the temperature of our rooms. Air conditioning in summer. Why can we run the air conditioning all day long and cool that thermal mass down, and then when we come home, again, we've got that thermal mass releasing or absorbing the heat out of the room and creating that coolth in the room. So, I think technology is moving very fast, and solar PV is becoming more and more affordable. Double glazing is becoming more and more affordable, and I think it's really going to transform the way we actually think about designing and building our homes.